works if I swipe the touchpad. Nice. Yeah, so to be on the same ground, let's first talk about what the electron correlation is. We all know that, but to be sure. So of course, electron correlation, you can see electron correlation as a difference between the exact energy and the energy from your model. So of course, we know that it's not a single, for a given system. For a given system, correlation energy is not a single unique number, but it depends on your reference, right? It depends how you have how you approximate your wave function with a model. So we can talk about Hartree-Fock correlation or correlation energy computed with respect to Hartree-Fock or constant DFT or CASSCF. That's what I talk about today. And of course, these correlation energies with different references are different numbers, right? So that's something to keep in mind. And we also know that no matter how many determinants you have in the wave function expansion, you will always miss something. And we can call this missing part a correlation energy. That's how actually we call it. And if you have a strongly correlated system, the idea is that you catch with your wave function the determinants or CSFs with the highest weights, right? So you want to capture static or strong correlation with the wave function. And the rest is typically left for the other method that should capture dynamic correlation. So dynamic correlation is related, from the perspective of the wave function, dynamic correlation is related to contribution of the determinants with low weights, which sum up to high contribution. So they make a difference for many chemistry important processes or energies like, energy barriers or covalent interactions or geometry. You cannot predict them accurately without correlation energy. But again, even if your wave function is given as a long expansion, if you have thousands of or millions of determinants, it's often not enough, right? You need to add this missing part. Okay, so I will skip this maybe CAS because it's a shame. You all know this. But just to introduce what I will talk about. So the correlation energy, I will talk the method that I will present is applicable. It's in general, it's exact, like the whole method is exact. The theory is exact, but then we make approximations, and in the end, the method is applicable to situations when you have orbital space partitioned into active, inactive, and W-occupied orbitals, which is a common situation because in most cases, the wave function method is defined or introduced in the restricted subspace of orbitals, which we call active orbitals. So what we are missing is the correlation between active virtual, active inactive, and virtual inactive. So the method will be adding these parts, right? Not, of course, the correlation within the active space, because it's already taken care of by the wave function, but everything else. Okay, so this brings us to the adiabatic connection. So I already said today that probably you have not heard about the adiabatic connection unless you have been exposed to DFT, to method development in DFT, because in DFT it exists under the acronym, or not the acronym, the name, adiabatic connection fluctuation dissipation theorem. And there have been many functionals which were many density functionals proposed in the recent years, like derived from this adiabatic connection combined with random phase approximation. So actually what people call now RPA in DFT has roots in adiabatic connection. So this is a common part with what I will talk about. Actually, we got inspired, let's say, or we learned a lot from the adiabatic connection in DFT when we were deriving the method for multi-configurational wave functions. So there have been a lot, already like 5-6 papers that we, maybe more now, that we published on this topic. So the method is implemented, checked, and works. Okay, so I will show you both the, not full derivation, but some main steps and then some applications. So the beginning is similar to the perturbation theory. You need, so you start with a model with the reference wave function, psi ref, and psi ref should be such that you know the H0 Hamiltonian. So you have to partition Hamiltonian, your full Hamiltonian H, into H0, which is the Hamiltonian for your reference function, and the rest, H prime. So H prime is like complementary parts to H0. There is a number here, alpha, which multiplies complementary part. So let's keep it in mind. So I will call alpha a coupling constant. So alpha varies from 0 to 1, so it takes you from non-interacting system when alpha is 0 to fully interacting system when alpha is 1. So by varying alpha, you are adding more and more correlation until you get full correlation at alpha 1. And those psi are everything which is indexed with alpha. It corresponds to H alpha, to the adiabatic connection Hamiltonian. So it's a function, it's parameterized with alpha. Okay, then I'm skipping some part, but it's very easy, it's kind of trivial to show that correlation energy, defined as the difference between the exact and the reference energy, is given by this integral. So we just need to use Hermann-Feynman theorem. So the integral is, so if you have an axis, let's say psi alpha, for each alpha you solve full Schrödinger equation, then you know an eigenfunction psi alpha. Then you can find correlation energy, but of course it's totally useless because if you are able to solve a Schrödinger equation for each alpha, it means you can also solve it for at alpha 0, so you have full solution. So this is just a first step, but we need to introduce some approximations. Everything else on this slide is still exact, because now the trick is to express all the quantities under this integral in terms of one electron reduced density function. So this will be our starting point for approximations, which is doable. Of course, Hamiltonian is involves 1 and 2 particle parts. So since it includes 2 particle operators, you need a 2 electron density matrix to compute these expectation values. But actually, there is a nice trick. It's from McLachlan and Ball paper from the 60s, but it's also quite trivial, if you know, that you can express 2 electron density matrix in terms of 1 electron properties. There's properties in terms of 1 electron reduced functions. So 2 electron is given by 1 electron density matrix, is a product of 2 elements, and 1 electron transition density matrix. But notice that there's a summation with respect to all states. So it comes from the resolution of identity, which you stick in between in brackets if you use second quantization to write 2RDM. Okay, so this is exact, right? We have expressed 2RDM in terms of 1 electron reduced density functions. Of course, we don't know them, right? Because they are given for each alpha, you have a different 1 electron function. So they're not known still. But then it allows us to rewrite the correlation energy in a compact form in the expression that is given here, where you don't have 2 electron density matrix, but on the transition density matrices and your reference density matrix. And this gamma ref is the 1 electron transition matrix that you can get from your reference wavefunction. So this is given. So now it's time to introduce so again, this is exact but useless because you'd have to solve a Schrödinger equation at each alpha. So we have to introduce approximations. Now, first, let's take a look at this delta term, because delta term depends on the difference of 1 electron density matrix taken at alpha 0. So when you have no correlation, or little of correlation, and your reference gamma. So a natural assumption, which is a reasonable thing, and this is to assume that when you change alpha, so you go from weakly correlated or uncorrelated system to fully correlated system, your 1 electron density matrix changes very little. Actually, we assume it doesn't change at all. So we fix 1 electron density matrix along this adiabatic connection path. And of course, this is a stupid assumption if, for example, you start with the single determinant and you have a strongly correlated system. Because then, of course, if you go with alpha from 0 to 1, then your density matrix changes dramatically. So it would be crazy to assume it's fixed or it doesn't change at all. But remember that this method is for multi-configurational wave function. We want to add correlation energy to CAS, or I name a few minutes later. So then your density matrix at alpha 0, your reference density matrix, is already correlated. So it already includes and takes care of the static correlation. So then it's reasonable to assume that if you go with alpha to 1, it will stay more or less the same. And we checked it. Of course, we don't even have to check that it's okay, this approximation. And then it's the benefit is that this delta term is 0. So we don't have to worry about any longer. But now maybe I will go back to. Now we have to take a look at this more complicated part, where we have transition density matrix elements at each alpha. So then this is a part where we learned from DFT, what people do in DFT. So the approximation we are employing is random phase approximation. In random phase approximation, this is one slide, but just briefly say what are the main assumptions. In random phase approximation, you assume that the excitation operator includes only single excitations. And then you can use the Rowes equation of motion. Of course, it's been known to write equations that yield or that give you excitation energies. These are these gammas, but also transition density matrices. This is what we need in our expressions of the first energy. So the transition density matrices or response will be described or approximated by RPA. But remember, this is only with singly exciting operators. So we are assuming that our excited states are approximated at the single excitation level. It already tells us immediately that we should take care of we should construct the wavefunction which we want to correlate so that it includes most doubly excited determinants, because this operator will not give it. It will not give us an access to doubly excited determinants for excited states. So this is a mathematical thing, let's say. We just needed some approximation for transition density matrices, and we use RPA, extended RPA for it. The good thing is that to construct these matrices A and B, you only need 1 and 2 electron density matrix. And this is actually a consequence of the fact that we only have singly exciting operators in this excitation operator. So this is the part where the method I'm talking about is very similar to what people do in DFT, but although it's not a DFT function in the end. Okay, so if we use RPA, random phase approximation, we can approximate transition density matrices with the eigenvectors of the RPA equation. And we end up with such an expression for the collision energy, which looks quite nice and compact again. We have to integrate it with this part with respect to alpha. But the function, this integrand, is a very well-behaved function. So actually, the fact that we have to integrate is not numerically is not a problem. Usually we don't have instabilities. So we need a low number of records. Okay, so the benefit is that from the computational point of view, the cost, that we only depend on 1 and 2 RDMs. So once you have the wave function, you compute 1 and 2 electron RDMs, and you plug them into the RPA equation, you solve it at a few values of alpha, and then you compute the correction energy. So it's given. But of course, as you could realize very quickly, RPA is quite expensive. It scales with the 6th power of the size, 6th power of the number of basis functions. So it's quite expensive. And we knew that in RPA, there is a way around to lower the cost to n to 5, but it cannot be easily translated, let's say, used for multi-reference, multi-configurational wave functions. So we had to figure out a new algorithm independently from DFT, which would lower the cost from n to 6 to n to 5. And actually, it's turned out to be possible, and it's given here. So I will just show very quickly. So we use the integration identity of this kind, introduce the integration with respect to frequency omega, and this allowed us to replace necessity to solve the RPA equation with a linear equation of this form, which is still empty. So there's no gain. We just replace one n to 6 equation with another n to 6 equation. But yeah, still n to 6. But if we use Cholesky decomposition of the integrals, and this is the crucial part in element in lowering the cost, the scaling to n to 5, you use Cholesky decomposition from Coulomb to Cholesky decomposition with Coulomb integrals. And now, before that, we have actually figured out that this C matrix, which is actually a linear response matrix, it can be expanded, can be Taylor expansion with respect to the coupling constant. And the nice thing is that there is a recursion relation which allows you to find the response function in order by order, recursively. So you solve, we find C0 and C1, and then Cn comes recursion. So very simple. You do just a few iterations, and you end up with the order in order that you want. But again, this original recursion relation was n to 6, and to lower the cost to n to 5, what you had to do, natural, to multiply the right-hand sides of the equations by Cholesky vectors. So then you lower the size, the dimensionality of the matrices. And everything, the most expansive matrix multiplications are scaled with the 5th power of the number of basis set. Okay, so it's again something mathematical, but in the end it's n to 5. Let's just count on, check that never do any n to 6 matrix multiplication. Great. So in the end, this is our final expression for the correlation energy, right? The benefits are, the advantages are that it scales with the 5th power. We have only n to 6 scaling with the number of active orbitals, which PT methods, it's very good, right? Because in PT2 you have higher scaling with the numbers of active orbitals because you need higher than second order density matrices. Here we only need 1 and 2 electron density matrices, so we keep scaling the 6th power with the number of active orbitals, which allows us to treat very large active spaces. I will not show very large today, maybe it will be 40 active orbitals, but we are now running calculations for 50, 60. There's also the question if you need that large active spaces, but if you do, you can apply these methods. So this is something you cannot do with perturbation methods. And it avoids instabilities. I didn't talk much about this, but actually this integrand that we had originally, it may have instabilities, which shows up as imaginary eigenvalues of RBA equations. But for large alphas, if you go with alpha close to 1, there may be some instabilities. But since we have expanded this integrand with respect to the coupling constant around 0, even if there are instabilities at alpha close to 1, we never hit that. So it's stable. But the instabilities is problematic for excited states. Okay, so this is a summary slide for those of you who lost track of what I'm doing, what I'm showing. So the goal was to find correlation energy, and the correlation energy is added on top of your wave function energy, right? So first you have to make the biggest effort and to solve your wave function problem. Once you have it, you construct density matrices, compute correlation energy, and add it on top. The method is applicable to this adiabatic connection to approaches where you have active orbitals and the rest, and you want to correlate the rest, the neutral orbitals, and also the inactive orbitals with active. So we have used it with CASSCF, CASSCF, DMRG, MCSCF. We haven't used it with RAS, but it's also doable, or GAS, the same. We have never used it together with these methods, but they are perfect, I think, because even if you have a few sets of active orbitals, then you can correlate these sets, right? You can do any kind of embedding. We also do embedding, so you can correlate embedding like the environment with the active system by the planets. And so to continue with the summary, right? So that's the expression for the energy, and to use it, you have to apply this recursive relation. And everything depends on 1 and 2 electron integrals, which you get from your wave function. And of course, 1 and 2 electron integrals, but this is obvious, so I didn't put it on the slide. Okay, so now a few applications, just 3. So the first is when we combine DMRG with AC, adiabatic connected with DMRG, and apply it to a few systems. I'm showing here iron porphyrin. That was a test. So maybe this is not the best example because we don't have very accurate reference. So we don't, in the end, we don't know which method is most accurate. But if we look at CAS, NFPT2, and CAS AC, so this is adiabatic connection, our method, and CAS PT2, we see that all correlation methods, this is a quintet triplet gap, they close the gap, right? Without correlation, the gap is 0.8 with this small active space. You add correlation and you close the gap. So they all do the same. They are closing the gap, which is good. Qualitatively, the methods agree. And in this example, the adiabatic correlation energy gives very similar results to NeFT2 for smaller active space 811, but also for larger ones. It's 3229 and 4042. The correlation, the gap is similar from, and it's often the case, not always, that we are close to NeFT2, but sometimes I will show also the example when NeFT2 gives some erratic results, and we don't. Passing by, we can take a look also at per density functional theory methods, PDFT. So for this case, this is actually what we talked, Giovanni. So the PDFT is based on density functional. So sometimes you may have surprises or unexpected behavior with respect to expanding the active space, that the results are probably inaccurate here. So actually, we are closing the gap comparing to uncorrelated method, to CAS, but too much. So the order of states is inverted. So the conclusion from this example is that AC performs on the same level as NeFT2. So probably, and we can go to larger active spaces than NeFT2. We go to 4040. The result is still 0.3 close to NeFT2. So probably this is, but we have no guarantee. We need something, a better method. But probably this is quite an accurate gap. Okay, another example is on organic biradicals, running out of time. So very quickly, we have also investigated biradicals based on cyclobutadiene, there also cyclopentadiene cation here with small active spaces, but they were sufficiently large. As I said, the active spaces must be such that you capture the double excitations or the highest determinants which enter with the highest weight in the wave function. So for these systems, it was enough to have 4 or 6 for the larger systems, active electrons and active orbitals. And very quickly, if we look at the results, this is the reference from DEA. So it's double electron attachment method with 4 particle 2 holes. It should be 2p from Piotr Piecuk. So he says it's almost full CI. So we trust. I think it's really very accurate, but also very expensive weeks to run calculations for this size of the systems with this method, but you can do it and you have the result. So RASPT2 is most accurate, it seems, among other correlation methods. So CAS is quite off. You see, it's 100% of the error. But with the adiabatic correlation energy, you add correlation energy and you squeeze the error to even below 20. In terms of EV, it's below 0.1 EV. So we were quite happy with the accuracy. So there are different variants, actually, I should promote them actually. And they are connected to the level of expansion in alpha. But if you do full expansion, you converge this series, then you get quite very accurate results actually. And the last was on systems which are very interesting or important, promising for OLEDs, organic light emitting diodes. So these are systems with inverted singlet triplet gap. As we know from Hund's rule, if you have 2 states, S1 and S2 states, triplet is below singlet. But there are exceptions to that recently found. This is the first molecule which was shown to have inverted gap where singlet S1 state is below triplet. And they are of importance for emitter. They can serve as very efficient light emitters. Okay, but our goal here was to investigate a few of, actually almost 100 of different derivatives of heptazine molecules, which is here. This is number 2. But the goal of this exercise or research was to check the effect of dynamic correlation energy of the gap. What changes the sign of the gap, if it's double excitations in the wave function or dynamic correlation that you add together with the correlation energy. So we found, and also the other motivation was to check the accuracy of the method, because we get very accurate results from multi-reference coupled cluster method. So we have found out that the static correlation changes the order of states. S1 is below T1, that has been known actually. But the effect of dynamic correlation is that it closes the gap. So a bit similar to this porphyrin example. And the AC method does very well. I'm not showing the errors here because the best results were when you include all pi orbitals, pi star orbitals in the active state, because pi star are sources of doubly excited determinants, and you want to include them by the CAS function and the rest with the adiabatic correction method. But of course, yeah, just this is the last. Of course, it's known that you don't need multi-reference methods for these kind of systems, and CC2, for example, does very well. But so maybe we can prove that it does very well because we compared it with multi-reference accurate results. Okay, so this is the last slide. So I presented, so I think this adiabatic connection is quite promising because there's some features, benefits over perturbation theory, like this low power cost, and the stability. You don't have, it's size consistent and intruder states. And the accuracy looks quite good. This for the cases that we tried. It's very easy to implement. As you can see, there is this recursion relation, so I think it's not very difficult. But the goal is actually that we will interface. The goal for the future. In the first shot, we are going to interface our code, so all the methods are implemented in our code, downpour, which is an open source. So we will interface it with MolCAS. Because what we need from MolCAS are density matrices and integrals, and the rest will be done in Gamma. Okay, and we acknowledge people from my group. Actually, Michał Habka has been a postdoc, but now he's in Warsaw. And Daria is a PhD student. And we have a very nice collaboration with Cholesky Institute, with the group of Libor Weiss. And they did a lot of work with us on adiabatic connection. Mikula, Matuszek, and Paweł Beran, the PhD students of Libor. Thank you for your attention. I'm sorry for